Good morning, friends. Last class we discussed about some adaptive control machining system. So what it means, adaptive control. So everything whatever is given by the program, it should be checked, okay, by means of some feedback devices or by means of sensors or by other means. We have to check whether your parameter which is entered in the program or which is given by the program is correct or not. Okay, otherwise the quality or the expected outcome will not be obtained, or the obtained outcome will not be checked. Okay, so you have to sure or you have to verify the parameters which is obtained or which is given by the program should be correct or not. So one method, by using the sensors and also by using some other electronic means, how we can measure the feed rate, speed, that and all you have specified. Suppose speed, if you specified 500 rpm, or feed rate if you specified 100 mm per minute, or 1 revolution, 1 mm per revolution. Like that, if you specify some feed rate, we should thoroughly check whether it follows the correct sequence. Okay, because it is governed by the code G90 or Z91 or Z98 or Z99. The command sequence which is given by that particular controller to that particular drive, so the drive actuates. So it is all the combination of electronics and mechanical combinations. But we don't know how the values are transferred. Okay, how the output is obtained, that we have to check. So one method is adaptive control system. By using sensor system, all the parameters will be controlled or governed or taken, and it is compared. Okay, compared with the set value. Then if there is any deviation, modify the controller, the input parameter, by increasing or decreasing the value, so that the required output value can be increased or decreased. Okay, so this is one method how all the values. So here it is given as cutter speed, feed, and also the air gap. Okay, everything is deducted by using this technique. Okay, so here this is a comparator control. Okay, the signal obtained through sensor by using a measurement of force and also the torque and speed, the rotary transducer, the linear information taken from the transducers, everything given to the comparator. Okay, here the set value will be there, so which is fixed as a standard. Okay, this is a measured input, both will be compared. After the comparisons, if there is any error, okay, with the set value, so that will be compared here. If there is any need, that will be changed in the feed rate controller. You can change the speed, you can change the force required, you can modify the set value, everything. Okay, so this is one control mechanism by using which you can check the quality of your output, so that the reliability of the CNC machines nowadays is very high when compared to conventional machines. What is the drawback in conventional machines over this? Accuracy. Okay, it does not depend on the job. Okay, so here whoever is done that particular work, the quality will not be changed, because this is everything is controlled by the machines. Only thing, you are going to enter the program, you are running the program or you are executing the program. But in conventional machines, what you are doing, you have to do your work. So this that is fully depends on the operator's skill. So the output of the product should be depends on the particular machinist or whoever handles that particular operation. But here it is not. It does not depend on the operator. Okay, all are controlled by means of a control mechanism. So the accuracy or reliability of the product output should be more in CNC machines. So last class we discussed this. So in general, there are two types of adaptive systems are followed in industries. Okay, one is adaptive control with optimization, and another one is adaptive control with constraint. Okay, so there are two adaptive techniques are followed. So depends on the requirement, depends on the quality which is expected by the vendor or by the consumer. We can choose any one. Okay, so the first one is what is meant by adaptive control with optimization. It optimizes the output or for a desired quality. It optimizes the parameter. Okay. Suppose if you are doing job in aluminium workpiece, you can increase the feed rate and also speed. So that will be optimized according to the material that you have used, according to the parameter that will be set. Okay. Suppose if you are doing a mild steel or in a heavy high hardened steel, the depth of cut feed should be very less. Okay. So that should be optimized according to the material. So here what optimization takes place, here the two parameters are calculated based on the tool diameter and also the workpiece material. Okay. So based on that the two values MRR and TWR. MRR is the material removal rate. It depends on the diameter of the tool, depth of cut and speed and feed. Okay, and tool wear rate, it also depends on the speed and also force given to the tool head and the feed given to the tool head. Okay, so by using these two parameters, the optimized value calculated. So based on that optimized value, the control parameters is set in that particular machine. So that it is called as a adaptive control with optimization. According to the required product quality, you can optimize or you can set the parameters. So that is called as a adaptive control optimization. So here the performance or the required expected outcome is optimized or is controlled by means of some of the optimization techniques. Okay, so the index of performance is calculated based on the two parameters, that is to reduce the machining cost, okay, and also to reduce the machine ideal time and also to increase the productivity. So the performance index may be calculated by using these two parameters, material removal rate and tool wear rate. So that is given by a ratio that is called as MRR divided by TWR. Okay. So at what rate the tool wear occurs and at the what rate the material is removed. So based on these two ratios, the performance index is calculated. If the tool wear rate is very low, okay, and also the performance index or the accuracy or quality of the workpiece is very high. Okay, so there is no frequently no need to change the tool because of the tool wear rate is very less. And also if the material removal rate is more, the productivity also increased. Okay, so based on these two parameters and also the ratio between MRR and TWR, you can find out the performance index. So based on these two values, the optimization value obtained. So based on the optimization value, all the parameters are controlled. So based on these two parameters, the speed is obtained. Okay, what will be the maximum speed that should be required for the particular operation, and the feed rate that is fixed by this ratio. Okay, according to the accuracy or performance required, the feed rate is also fixed. That is fixed to optimized value. This is one block diagram for adaptive control with optimization. So here the general CNC system there, okay, it resembles the conventional machining operations. We have a NC system. NC system in the sense that we have a controller which has the PLC and also the integration of PLC, microprocessor, microcontroller and every hardwired system with the drive system. Okay, and by using a command or by using a program, by using Z code or M code, it is programmed to run or to execute the desired drive, that is machine tool. Okay. So because of the code transferred from the controller to the drive, the required operations perform. If there is no sensor, if there is no feedback devices, then we can't check the quality or we can't check the output that is obtained by the program. So the sensor is placed to measure the speed, feed and all. So all parameters is measured to check or to verify. Okay. So how it is verified or how it is fixed or how the values are optimized. Okay. So the measured value come back here. Okay, here we have one control optimizer here. What it is set here, according to the two value, tool wear rate and also material removal rate, we have a general formula to calculate that. So by default, that will be calculated by the processor itself. Okay, according to the material, according to the thickness of the material, according to the tool you are using. So based on these two parameters, this will be calculated. Okay, for a particular value and also for a particular material, what will be the maximum limit? So that is already fixed to the systems. Okay, so that is given. Suppose if you are using a mild steel, if you are using this much speed, so this will be the rate. Okay, up to this speed, this will be the rate. And also up to this speed for this material, this will be the rate. So that kind of maximum limit is fixed there. So the measured value should be less than that of that. Okay, if it is more than that, what happened? Unwanted or unexpected thing may be happened. The tool failure, workpiece quality is not obtained. Okay, so based on these two demerits, some demerits, the constraint limit is set here. Okay, so these two values are calculated and these are set. Okay, this value should be less than that of the maximum limit. So that will be calculated by using the performance computer. So in this here the performance index, that is PI, have been calculated. So based on that value obtained or PI value, the optimization computer calculates the or suggests the optimized value. Okay, so for this particular operation, what will be the speed, what will be the feed, what will be the force that are to be given. So everything is calculated here, and this will be interfaced to the controller. So the controller, whatever may be the values that are given in the program, that will be optimized automatically. If the speed is set 3000, okay, for the particular operations, the speed required is only 2000 is calculated. What happened? By reducing the speed by means of override, so the value, the speed value automatically reduces. Okay, but the program executes 3000 RPM, but the controller reduces the speed override from 100% to some percentage, so that it is obtained 2000 RPM. So this optimized value is obtained. This optimized value is not constant for all the operations. Okay, for each and every operations, the values are executed. Okay, the tool wear rate and material removal rate are calculated. So based on these two values, these value have been fixed or set to the controller or fed to the controller. So the controller runs that particular feed. So that in all the CNC machines we have a speed override function and also feed override function. Okay, so the feed and speed can be reduced and also increased without changing in the program. So that is the main advantage of providing that override option in CNC. So this is one type of control system that is called as adaptive control with optimization. So the adaptive controller consists these circuits, 4 circuits. This optimization computer, performance computer, and data reduction subsystem. So and the interface. So these 4 subsystems consist or makes the optimization process. It find out the optimized value, and that value fed back to the programmer or controller to control the particular parameter. So that is given again here. So how the MRR and TW are calculated? So these are all two simple formula. Based on that, the MRR and tool wear rate are calculated. So the MRR may be called as a mu. So that is depends on the width of the cut. Okay, that is the cut area equivalent to diameter. Okay, how much width is obtained, and also depth of cut, how much depth is given. Width maximum is equivalent to diameter of the workpiece. Okay, depth that is fixed by the programmer, and S is a spindle speed. So based on these three parameters, the material removal rate may be calculated. Okay, at what rate the material is removed. So based on the depth of cut, based on the width, and based on the speed. So how much speed it is moving. So based on that, the material removal rate are calculated. And also tool wear rate, the same formula. Okay, so K1, K2, K3 are some constant value for a particular material that is suggested by the tool manufacturer. Mu is a material removal rate, and T is a tool temperature that is produced during the operation, and d theta by dx is the rate of change of torque. Okay, so because it is revolving at a particular speed, bottom workpiece is stationary, the tool is rotating. Okay, so the rate of change of torque at the tool tip, that is calculated based on the measurement, based on the value that is obtained through sensor. So this value will be calculated. So based on this, tool wear rate is find out. Okay, so these two ratio or two parameters, MRR and TWR, is required to measure the performance index. Okay, so based on this PI value, the optimized values is sent back to the controller. Okay, so this is the adaptive control with optimization. So the next is adaptive control with constraint. So this is a second technique. In a particular operations where you can't measure the tool wear rate. Okay, suppose if you are using a ball and mill cutter, you are measuring the surface, you are creating the null surface. It means that it is a smooth surface or fine finishing operation. In those cases, if it is a spherical face tool, that is a ball and cutter, it is very difficult to measure the tool wear rate. Okay, because the depth of cut is almost very less. Okay, and also the tool wear rate you can't predict at all. So in those case, what you can do, what will be the maximum value or what will be the constraints that are given. For that particular constraint, you have to set all the parameters. Okay, so in the previous also we have the constraint, but according to the job, according to your required or expected outcome, the parameters are set. But here, what will be the maximum value? For that value, you have to set all the parameter. Okay, so that is the constraint that are given. For that particular operations, for that particular constraint, you have to set all the parameters. Where you can't measure or where you can't set the tool wear rate or all other parameters that are required. So that is called as the adaptive control with constraint. Okay, so this is a second technique. You have to set the constraint for the constraint which is calculated or which is fixed for that particular machine or for the particular workpiece. Okay, so here in addition to that MRR tool wear rate, that is not calculated here, you have to measure the vibration and torque. By using vibrations, you can use any sensor to measure that vibration, and torque, by using a torque sensor you can measure the torque. Okay, so based on these two parameters, that value is observed. Okay, and also the measured value is compared to the constraint value, and again the constraint value is set back to the program value. Okay, so that is called as adaptive control with constraint. So this is a block diagram. This is a big block diagram, so that it is split into two diagram. Okay, so in the first diagram we have a machine. Okay, we have a MCU, that is machine control unit controller, and this is a drive. So this is interfaced with the controller to drive. So that is a normal CNC system. So that is a servo drive, machine tool, spindle speed drive, everything. So these are all the line diagram of a CNC machine. Okay, tape reader in the sense, tape reader is in olden days we are using a tape to record the program. The program is read from the tape and it is executed in the controller and the machining operation takes place. So nowadays we have the memory inbuilt in that particular machine controller, so that memory is used. Otherwise we have the RS-232 cable or communication between system is possible. So nowadays by using a USB drive or by using external cable connections, the programs are transferred. But in olden days those communication is not available. So in those days they are using tape reader, magnetic punched tape or ordinary tape was used to record the program. So this is one kind of CNC system. That feedback you can check by using a transducer, linear transducer, and also the movement or the rotational speed that you can calculate by using a rotary transducer. Everything is measured. Okay, the force, spindle load, by using a load sensor you can measure. Okay, spindle speed by using a RPM measurement you can measure. Okay, torque and vibration by using a separate sensor, the torque and vibrations are measured. Okay, so it is fed back to the adaptive controller. And also externally we have given the constraint limit for that particular workpiece. Suppose we are using a end mill cutter for 15 mm dia, and for the workpiece we are going to machine. For this we have some maximum constraint limit. The speed should be this much, speed should be this much, vibration for this particular operation should be this much. Okay, and also the torque for this particular tool over the material should be this much. So these are all the constraint limit that is there all for a particular operations or particular tool. So that is given by using this constraint limit. Okay, so the constraint limit for a particular operations we have to set, and that set value is set back to the program. Okay, so that set value, that is the maximum constraint limit. So that is here the adaptive control we have given the constraint limit. Okay, that is maximum constraint, and also the part program that is given from the tape reader we have taken. So this diagram is extended from that diagram. Okay, the previous diagram. So this part program this is coming from the tape reader and all. So in CNC machines we have a machine memory. This is a maximum constraint limit. So this is an optimizer. Okay, it compares that value, measured value, the set value. Okay, according to the particular operations, if there is any deviation, what happens? The value is set to the maximum constraint value. So that program is changed to that maximum value, so that the speed gets increased. Again, the values are measured, the increased value. Then both are compared. If there is any deviation, again it modifies the program. Okay, so this measured value in the here. Okay, this is controlled. Okay, this is controlled, again sent back to the controller here. So it's sent back to machine tool and activator system. Activator system in the sense this is a feedback controller. So it obtains that value and modifies the program and it executes in the drive. Okay, so this is a adaptive controlled system with the constraint value. The required workpiece is machined. Okay, the quality is obtained. So this is another system called as adaptive control with constraint. So what are all the constraint limits that are available? Maximum and minimum spindle speed, maximum allowed torque, that is torque value, and chip load, the force that are given, down permitted feed rate. Okay, impact chip load. In some cases chip breaker is available. Suppose where the continuous chips are produced. Okay, so in those cases we have to reduce the load on the workpiece to reduce the chip thickness. Okay, so in fact chip load also you have to give, and also maximum allowed vibration. Okay, these are all the constraint limits. So based on these limits, the value is set to the program and the program is executed for the constraint value. So this is the important constraint used in the ACC. Okay, so the adaptive control is very important topic. Nowadays in both the techniques are used. Okay, adaptive control with optimization and adaptive control with constraint. In majority cases, the adaptive control with optimization is used because it optimizes all the parameters. Okay, where it is not possible, you can use this adaptive control with the constraint. In those cases, the values are set to the constraint value, that is maximum value. So this is not always possible. But in many industrial operations where you can't predict all the value, the ACC method is used. Okay. Otherwise, what you can do, you can go with adaptive control with optimization. The last one is computer assisted part programming. Nowadays, what we are using is called as a general CNC programming. It consists of the code having G code, M code, and followed by some parameter. Okay, coordinate positions X, Y, Z or A, B, Z, and tool you can change, speed you can set, speed you can set, and some other parameters may be set for executing that program. Okay, but this is nowadays what we are using. The program is the latest generation CNC machines program. But in olden days, that is while starting the CNC machines, this type of program was used in a particular NC machines, and also while integrating the NC to CNC, this type of assisted part programming was used. So in 1965 to 70, the computer was introduced. Okay, during those time, some programs are used to assist the computer. Okay, to execute some control from the computer, so that the computer was used to control the particular CNC machines. So in those cases, the special type of program was used, that is called as a APT, that is APT language, that was used to support the some kind of program. In a numerical control, we have a numerical letters to control all the operations. But here, after inventing the computer is used to control everything. So how the computer controls? We need some special commands. Okay, by using that command, the required operation is communicated to that particular controller. So what are all the programs that are executed during those times? So that we are going to discuss here. That is computer assisted part programming. So one famous technique which was used here is APT, that is APT language. So automatic programmed tools, or this may be called as automatic positioning tools. Both are same. Okay. So the automatic programmed tools is the language which was used in olden days, that is while start of the computer generation. Okay, where the computer is integrated with the controller to control all the parameters. So to control, the control parameters were required. So during those time, the APT language was introduced to control, to give the parameters. Okay, so it like a command executing operations. If you give that particular command, that command is executed in the controller. So what are all the general commands that were available there? Okay, so this is the automated programmed tool that was developed again by the MIT, because the controller was manufactured by the MIT. So they know what type of operations that should be executed. So for their controller, they developed one program that is called as APT. Initially it was used to control 3-axis machine. Later it was extended for all axis machines. Okay, so we have 4 types of statements in APT language. Okay, so these are all some examples are given. So based on this example, if some diagram is given, you have to write the program. Okay, so the first one is a geometry statement. So geometry statement in the sense, according to the geometry, first we have to create the geometry first. Okay. So if you want to create a particular geometry which is to be executed in that particular program, so some commands are required. So these are all some command prompt. Okay. Point in the sense you have to give the command. So you have to specify the start point. Okay. If you want to specify point in that controller, you have to give the command like this. Point is the coordinate points. Okay. If you want to specify line, L1 is the parameter name, line is the command. We have to specify 2 points, front and 2. Okay. That is P3 and P4. So P3 and P4 already specified by the point here. So the point can be specified like this, P1 and P2. So that P and P2 can be called here. Okay, so P3 and P4. So line 2, instead of giving 2 points, we can use this one. Line P5 and parallel to L3. Okay, so some relation. Okay, how you can generate a line. And also this is a plane, generate a plane which is passing through 3 points, P1, P4 and P5. And this is plane 2 parallel to plane 3. Okay, C1, that is circle with the center and radius. Okay, that is center should be specified by means of a point, and you have to specify the radius. So these are all some of the geometry commands. Based on that, you can generate the geometry. Okay, or you can give or you can communicate your geometry to the controller. So you have to specify this. So based on these parameter or command that are given, it forms some geometry. Okay, so it forms the outer boundary of the particular geometry. For that outer boundary, for machining the outer boundary, the program is used. Okay, so this how the motion takes place, how the tools are moving. In a normal CNC machines, the center point is moves. No? So based on here also the center point of the tool moves. So that is the reference point is center point of the tool. If you specify point P1 and P2, the center point of the tool moves from point 1 to point. If you want to offset, you have to change the offset value. Okay, so that is there. So this is one block diagram how the tool moves. So next one is a motion statement. You have to specify these to move the spindle or tool or workpiece or work table, everything. Okay, so go to point 2. So wherever the tool is there, that will go to that particular point. This is from tangent. Sorry, this is target. Okay, so front means you can give the start point position. Okay, so suppose the tool is here. If you want to specify the tool from this point to this point, now the tool is in a home position or somewhere else. If you want to move from here to some value, so that is this is value from to this point. Okay, suppose if the tool is here, directly if you want to go to this point, you can use go to option. Okay, if you want to move from some other location to some other locations, you can use the second statement. And point to point motions, go to that particular point. Okay, one point to another point. Then this options go DLTA. So this is for drilling related operations. Okay, so drilling, wherever you want to make drilling, you can use this code for making drilling operations. Then contour motions. Contour in the sense pocketing cycle. So continuously if you want to move, you can use this. This is a go LFT means go left. Okay, this is the left side movement. Go forward directions. Okay, go up or go down. So these are all the commands to move the tool. So it looks like a order that are given to that particular given. Okay, a oral statement if you give, go forward, come to this point, come to this point. If you give that particular operations, executes. So the complicated objects we can't give by using this. So some simple statements we can obtain. Okay. These are all some of the example for motion statements. So who says time up? You come at 8:10. Most of you guys. Post processor statement. This is to execute some other options. Okay, coolant on off kind of things. This is a machine, that is machining operations. It may be turning. It may be some other machining operations. Turret, that is tool turret on in case of turning. In milling, tool head is tool post is on. End of the statement. Rapid in the sense rapid movement. Feed rate, you can fix the feed rate here. Spindle speed, that is spindle rotation, either clockwise or counterclockwise. Spindle speed you can set. So these are all some post processing statement. And the next one is the auxiliary statement. Auxiliary statement which was required is to print your program, what you made. That program, entire program, if you want to make, you can make the print. Okay, and you can specify the cutter diameter, everything, and tolerance value you can set, inside tolerance and outside tolerance. This is the inside tolerance value, this is outside tolerance value. Finishing value you can set. Okay, how much accuracy you want to exercise, and you can save the part number. So these are all to help the file or help the program, save the program, to record the program, to print the program, okay, to set some parameter, everything. So these are all the some of the commands that were used in auxiliary statement. Why